Hi, welcome to a Superspace Theory video, and I'm going to be looking at how Superspace Theory can help us to understand some of the unsolved issues of physics and cosmology in a new way. This will be a little bit of a vlog type reflection video in the sense that I'm not going to be very organized. I'm just going to be looking at some ideas and some stuff on the internet and reflecting on it. So I'll be using articles under fair use policy, just bits here and there to make the point that by understanding the core principles of superspace theory, namely that size equals distance at fundamentally smaller levels of physics, as well as understanding the greater multidimensional block universe of superspace and how fields and heavenly bodies exist in these different layers. So rather, heavenly bodies and particles exist within these various fields in multidimensional space, and how this overall picture can help us to completely change our perspective on some of the problems we have in physics and cosmology. And so let me begin here with an article, 7 Biggest Unanswered Questions in Physics, and one that I found interesting, number 1 in this list, is literally, what is matter made of? And so it's basically saying how, we originally understood matter to be composed of atoms. Atoms were then seen to be composed of quarks, going down to the Higgs boson. And so with superspace theory, and I'll actually move down to the end here with the unified. Oh, no, that wasn't quite what I was getting at. I think perhaps, but I'll have to look at this. So when we're talking about matter and looking at a smallest fundamental particle, or as in superstrings would say, a vibrating string, quantum loop theory would say, these quantum loops. The problem is that we are looking at physics as going smaller and smaller and smaller in the subatomic realms, when in fact, at some point, we are moving in this fourth spatial direction of the fourth dimension when we go inward into what we think of as the realms of the very small, but which are actually a fundamentally different fourth spatial direction. So in my book, Superspace Theory, as well as my videos, one of my graphics that I show is this one, where I look at how, if we use a two-dimensional analogy, like in the Flatland book and is often used, we look at our 3D space as two-dimensional in order to understand these things. You could see it as a flat sheet, and so it's like what we're doing, we're seeing matter and we're looking inward, we're seeing it as composed of smaller and smaller and smaller levels, but small is the only concept we have here, so we think things are continually getting tinier and tinier, whereas in superspace theory, or in the Flatland analogy, understood fully, you can look at our universe as a 2D sheet, but instead of seeing everything as getting smaller and smaller, at some point, as we go inward into these smaller levels, when we move into fundamentally smaller levels of the quantum realm, subatomic physics, we curve in a fundamentally different fourth spatial direction of the fourth dimension. So things are no longer getting smaller at this point. We're moving into fields of multidimensional space that lie alongside our own 3D universe. And this is what we think of as the realms of the very small. And these fields would be where quantum phenomena, quantum particles, which are actually holes within fields, would be located. So you could have a nucleon here, you could have a quark here, you could have a Higgs boson here, you could have a string here if that's what was the next level down, inward, and you could have quantum foam here. And so instead of this being smaller and smaller, it's literally moving in this fundamentally different fourth spatial direction. And this all takes place in what I call the block universe or superspace. And so again, if you look at our universe as a 2D sheet, and you see that there are these fields lying alongside our universe that move in this fourth spatial direction or dimension, and this is where fundamentally smaller particles would be located. All of these fields exist within this greater block universe. Now, the boundaries here are not, necessary. The fields could potentially go outward to any extent, but that's just for clarity in the picture. But so we see that there's this fundamentally different direction within a greater multi-dimensional superspace or block universe. And so when we understand that, we see that we are not going to find that smallest particle, that smallest point particle. Quarks lie in this fourth fundamental direction, and so would, let's make a few more layers here, so would the Higgs boson, so would superstrings in this different direction. So they're not actually smaller, held inside of atoms, an atom with a nucleus, let's make it big, with quarks inside, with, bosons, and then superstrings inside, getting smaller and smaller. It's actually lying alongside our 3D space in this fundamentally different direction. So we are not going to find a smallest particle or string or whatever. We're going to keep going in more energetic levels or fields of space, and forever finding more energetic phenomena as we go deeper. And so there is no end to that search, and that's one of the predictions of superspace theory, which obviously would only play out in time or be, confirmed over an amount of time where we continually see new and more energetic particles as we break apart or go deeper into these fields of the greater block universe. And so that shows us the answer to our never-ending quest for a fundamental particle, that is not going to be found. It's not going to actually happen. And so that's one of the things that we can look at in a new way with the perspective shift allowed by superspace theory. And I think one of the other things, well, there are a couple other things. The arrow of time and entropy was one, but actually the one I wanted to look at that I find really interesting is the idea of quantum entanglement. So quantum entanglement, let's just read this, is the phenomenon that occurs when a group of particles are generated, interact, or share spatial proximity in such a way that the quantum state of each particle of the group cannot be described independently of the state of the others, including when the particles are separated by large distances. So when particles become entangled in this way, you can separate them by any amount of space, and then you affect one, and the other is immediately affected. So measurement of physical properties such as position, momentum, spin, and polarization performed on entangled particles can be found to be perfectly correlated. A pair of entangled particles is generated such that their total spin is known to be 0, and one particle is found to have clockwise spin on a first axis. So this gets a little complicated, but the point is the other particle will match it exactly, and wave function collapse of that particle will be matched, in some way by the other particle, exactly and instantaneously, meaning that in a sense it's like the particles are the same particle, although they are separated by all the space. Now, when I was looking at this, I found some interesting graphics. So this is just a artist's rendition. So we see connectedness of two entangled particles, right? So that's an artist's rendition. So we have a particle here, and we have a particle here, and this is the entanglement. Okay. So we don't understand this. Einstein called it spooky action at a distance. But we have observed this to be an actual effect. There is enough experimental data to actually say this is a real thing, but we don't understand how it can be, right? Well, what superspace theory shows us, so if we remember our picture of our own universe as a 2D, sheet in a lower dimensional analogy with spatial dimensions or fields lying alongside or under it, which is the direction we think of as the realms of the very small. Okay, so this is us, our universe. So say we have these two particles that are quantum entangled, if that's how you say it. Okay, so like this image that we had, let's see. So we had this image, so this is the, if you can see my mouse, this would be the entanglement. They're connected in this mysterious way where they are basically acting as one. Okay, so what we just have to see is that instead of looking at it like this picture, right? They're connected by this string which we can't observe. Why is that so mysterious? What we just have to see is that these two particles are actually one particle. So let me draw two sheets, but these are the same 2D space of our universe. These aren't sheets lying alongside each other. This is the same our universe, us. Okay, so in the normal understanding, you say these two particles are somehow entangled. But in superspace theory, you can say when two particles come together, they do actually become one in this sort of, quantum or electrical or energetic or, in terms of the fundamental nature of the particles, they do essentially become one. That's what entanglement is. So when they start to separate, we're seeing them as separate in this particular field, but actually this entanglement means they continue to be one, but the entanglement is deeper down. So it's like if you imagine a snake with two heads, we'll make little tongues, which aren't at all necessary for the analogy, right? So here's this field, and like in flatland analogies, the heads are here in this two-dimensional field, but the body goes deeper, right? So it goes down. If this is a 2D analogy, it would be going down into the third dimension, so we would only see the heads, and yet if you poke this head, this one over here would go, ouch. Because it's the same creature, right? So that's actually what quantum entanglement is. Here's another graphic, and you have two particles, and I'm just using this briefly under fair use policy. I do not own this graphic. It is not my graphic. So you have these two particles, and they're, entangled in some mysterious way. But actually, if we see it that this entanglement is actually looping down beneath our field of space, that's all we have to see. Then these particles, it means the entanglement is a connection that remains. They are actually still one phenomenon. They're still the same phenomenon. Like this. And that does at least suggest an answer to quantum entanglement, because no matter how far apart you pull these two snake heads, or particles, as it were, the body is still there. It will just stretch and stretch. So they could be incredibly far apart, and they're still one. So you still would poke this, and this would still say, ouch. I can't write with my mouse, obviously. So that's another potential solution, or at least it leads us in the direction of a new way of seeing it when we understand that our universe has these deeper fields lying alongside or underneath. And then there was that final well, there's actually a bunch of things that I think could be answered by superspace theory, but I didn't want to go into them all in this video. But there was the whole idea of entropy in the arrow of time. That's actually a pretty complex one, but I'll just very briefly touch on this. So we covered quantum entanglement. When we talk about time and the arrow of time, when we experience time as directional, that often has to do with the second law of thermodynamics, that things are breaking down. First, the concept of entropy, it establishes the concept of entropy as a physical property of thermodynamic systems. And so let's look at entropy. Second law of thermodynamics is central to the second law. The entropy of an isolated system left to spontaneous evolution cannot decrease, essentially meaning that the entropy will increase over time. And so when we look at the arrow of time, that apparent arrow has to do with the fact that we experience entropy progressing in one direction. Things don't move in the other direction, and so we have this sense of an arrow of time. Well, all of this is true, but we're just not understanding why it's true. And again, it comes down to the exact same thing, which is understanding the fields of space in the block universe. So in the block universe model, one of the things that I talk about in the book is how the block universe is moving. So this big arrow here has to do with a moving block universe. So in superspace theory, these fields move from the more entropic, and at the bottom here you have the most energetic. And so this energy is pushing through the fields of the greater superspace or block universe, and that creates an overall motion, and that overall motion is time, as I show in superspace theory. So there is an actual motion or direction, a directional motion of time. Because these fields, you can either look at it as these fields are moving in a direction, or that the energy moving through these fields means there is a directional motion. So in superspace theory, if you look at our universe as a 2D sheet and look at the fields lying beside or under it as moving in the direction we think of as the very small, this motion is the motion of time, motion through the fourth dimension. The fourth dimension is this direction. It's the direction of small. When we curve out of our own familiar universe into this fundamentally different direction, that's the fourth dimension. But time is the motion through that fourth dimension. And that motion is directional. And so if we look at this as the field of our universe, and this is very hard to comprehend in 3D, you know, thinking of our universe as three-dimensional space and trying to understand this, it's very, very difficult, which is why it's necessary to look at it in 2D. But this field right here is moving, or at least the energy within it is moving, and that's complex, but it really comes down to essentially this field, which is made up, in a sense, of energy. All of these fields are. So that's why we have wave-particle duality, waves of energy, and then these energy holes, which are particles. And I'm not going to get into all of that at all. But the field of our universe is moving through what we think of as time, which is actually physical motion through the greater multi-dimensional block universe. It is physical motion through the greater multi-dimensional block universe. So time is actual real motion. Now, as far as entropy, I have two things to say about that. One is that things don't always break down if we think of energy as coming in to this field of space from deeper fields. So the Big Bang model says it came in once and energy does not come in. It's a closed system. But superspace theory posits that energy does continue to come in. So that actually questions the second law of thermodynamics in terms of it being absolute. But the other point, the bigger point I wanted to make is if this field is moving, you can look at it almost as this jiggling, moving field, but also that the bodies in this field are not just isolated to this 2D field, they're connected to deeper fields. That's one thing that I get into in my book, but haven't got into in depth, is that these fields are not just completely separated, they do connect and affect each other. So that's why we have the energetic interactions between particles, which makes us believe particles are inside of other particles, but they're actually just interacting within these discrete fields, but they are interacting. And so as our field of space moves, these bodies and matter and everything is affected by its connection to these fields that are, you could almost say, being left behind. So in superspace theory, to put it simply, the breakdown of matter can have to do with the fact that space is moving in this fourth dimensional direction, and it affects the matter within that moving field, especially if that matter is sort of embedded in deeper fields. That's very complex, but that's just a sort of a perspective shift that can help us to understand entropy in a new way. But that is very complex, and I won't try to get into that in detail. But I'm mainly just wanting to show that this essential idea of the direction we think of as being small actually being a direction in a fundamentally different fourth spatial dimension or direction. And I'm confusing myself a little bit because I'm trying to pull up a new sheet while I talk. But that basic idea that sees our universe as a field of space with underlying fields moving in what we think of as the direction of the very small, and that this whole thing is moving from the energetic to the entropic, these basic concepts right there can completely shift our view, including that heavenly bodies, like black holes, are all holes within the field, and fundamentally smaller particles, quantum particles, are also holes within fields, rather than the excitations of quantum field theory, although that is one way of looking at it. It's better understanding these as holes within the different fields. Those three things, that size equals distance, that there are these fields of space moving in the direction we think of as the very small, and I'm outside, so there's some noise from construction, but I'm about to finish anyway. And also the heavenly bodies and particles as wholes. All of these taken together can really shift how we view some of the unsolved questions of physics. Thank you very much for watching the video.